After studying this module, you shall be able to understand what are tropones and tropolones and their structure, their nomenclature, and how are these molecules synthesized, their properties, chemical as well as biological, and some of the natural products containing these moieties. Now let me introduce these molecules to you. Tropones and tropolones are important in organic chemistry, and it has been developed in recent years, and collectively they are called non-benzenoid aromatic compounds. You all know that aromatic compounds, what we have been thinking about is benzene ring. If we talk about smaller ring compounds such as cyclobutadiene, this is still unknown and it's generally assumed to be too strained to be stable. If we talk about the larger ring compounds like cyclooctatetraene, it exists in puckered form, the planar form of which would be necessary for aromaticity. So cyclooctatetraene cannot be aromatic and it is highly strained if made planar. So among these systems, we may thus be focused on the 5 and 7 membered ring systems, which may be aromatic. For example, these are the anions, radicals and cations of the cyclopentadiene and cycloheptatriene. In these figures, we can easily see that whether these molecules are aromatic or non-aromatic, we must have Huckel number electron present in them. That means 4n plus 2 pi electrons. Of the system mentioned, only the cyclopentadienyl anion and the cycloheptatrienyl cation satisfy this condition. So if we talk about tropone, or which is iopic, which is known in the iopic nomenclature as 2,4,6 cycloheptatriene 1-one. This is a non-benzenoid organic compound and it is aromatic in nature. Tropone consists of a ring of 7 carbon atoms, which is very much equivalent to cycloheptatrienyl cation. It has 7 carbon atoms with 3 conjugated alkene groups and a ketone group. The tropone moiety can be found in biomolecules such as cholecystokines, which are generally used as medicines to treat gout, stipitate acid, and hinokitiol, which is also a derivative of tropolone, and actually it is a natural monoterpenoid found in the wood of trees. This hinokitiol has inhibitory effects on Chlamydia trachomatis, which is a bacteria responsible for spreading STDs. Shown here are the structure of tropone and tropolone. The difference between the two is tropone is a simple cycloheptatriene with a ketone moiety, whereas tropolone is a derivative of tropone itself containing a hydroxyl group in addition to the ketonic moiety. The iopic nomenclature of tropolone is 2-hydroxy 2,4,6 cycloheptatriene 1-one. The nomenclature of tropone and tropolone. Let us see how they are named. The trivial name tropolone has now been sanctioned by such wide usage that it may be considered as generally accepted. Its iopic name is 2-hydroxy 2,4,6 cycloheptatriene 1-one. As the name indicates, the carbonyl oxygen is always taken to occupy position 1 because it has a higher priority than the hydroxyl group. And then the hydroxyl group is given the position 2 and the rest of the substituents are named accordingly as shown in the figure. We have numbered the carbon here starting 1 with the carbonyl carbon and number 2 as the hydroxyl containing carbon, and rest we go cyclic manner in a clockwise manner to further give the numbers. To make possible the assignment of a single unambiguous name, number 1, that the formula is used which leads to the lowest total number assigned to the substituents. That means whenever we have more substituents apart from the hydroxyl in the carbonyl group, the numbers should be given to those substituents such that the total of those numbers should be minimum. For example, in compound it is named as 6-methyl 3-phenyl tropolone and not as 4-methyl 7-phenyl tropolone. Similarly, The second point is where the above rule becomes indecisive, that substituent which is named first receives the lower of the two possible numbers. For example, in compound as shown in the figure, it is named as 4-methyl 6-phenyl tropolone and not as 6-methyl 4-phenyl tropolone. The tropone name is used to designate 2,4,6 cyclopentatriene 1-one, but the use of the other trivial names has been kept to minimum. Now, various classes of tropolones. What are the various classes that we will know now? There are a few natural tropolones known at present which can be divided into 3 groups. First one is isopropyl tropolones. These are the simplest of tropolones which occur in several conifers. Conifers are like cone bearing plants, and all conifers are belonging to the family of Cuperesaceae. Examples of this class are alpha, beta and gamma thujaplecin as shown in the figure. These thujaplecins are the chemical substances which are isolated from red cedar tree. They are very well known for their potent antifungal and antibacterial properties. They are also known to have some potent antioxidant properties. Figure shows you alpha, beta and gamma thujaplecin, and they are all derivatives of tropolones having isopropyl moiety at different positions. The second class is belonging to hydroxytropolone carboxylic acids, and they have found only in mold species, for example in the penicillin family. The third class of tropolones are colchicine, and a few very closely related compounds have been isolated from various Liliaceae, particularly from Colchium autumnale, which are nothing but the meadow saffron or autumn crocus and related species. Now, how can we synthesize these compounds? The first synthesis is from cycloheptaoxone derivatives. This is nothing but a dione derivative of cyclic heptane. We can say it is from 1,2-cycloheptane diones. The bromination of 1,2-cycloheptane dione provide mixtures of products which give tropolone and its bromo derivatives with the loss of hydrogen bromide on warming. This is shown in the figure in front of you. We can see that we have 1,2-cycloheptane diones. It is brominated with N-bromosuccinamide in presence of chloroform, and the mixture of products is then heated at 90 to 100 degrees Celsius to get tropolone and a bromo derivative of tropolone. The synthesis of substituted tropolones by this method requires a source of substituted cycloheptanones. 2 methods have been widely used for their preparation. Number 1 is the cyclization of appropriately substituted subearic acids, and number 2 is ring enlargement of the corresponding cyclohexanone with diazomethane. Diazomethane is very well known in organic chemistry to insert one carbon atom and mainly used for ring expansion. The conversion of diketone is always affected with selenium dioxide. The ring expansion of isopropyl cyclohexanone with diazomethane fails, but the desired ketone, which is shown in this figure, is obtained from ring expansion of cyclohexanone by the reaction with diazoisobutane. Its oxidation by selenium dioxide in ethanol yields rather than the simple dione, but this loses ethanol during the remaining stages and affords the desired product. The other method to synthesize these derivatives are from 2-hydroxy cycloheptanone. This is nothing but, you can say, it is completely saturated form of tropolone, where we have cyclic heptane structure with a ketone and a hydroxyl group. So these unsubstituted tropolone has been obtained from diethyl pimelate by acylene condensation, and it gives the ketone followed by bromination. The bromo derivatives leads to smoothly to tropolone after the bromination of diketone, which therefore cannot be an intermediate. This is shown. Diethyl pimelate is first converted to the ketol, and this ketol is brominated to give you a tropolone derivative. Another method to prepare these tropolones is from cycloheptanones. Cycloheptanones as well as cycloheptenones and cycloheptadienones, all of them can be used for preparation of tropolones. The bromination of cycloheptanone provides an intermediate tribromocycloheptanone as well as tetrabromocycloheptanone. Both of these intermediates can be isolated, and furthermore their bromination in acetic acid provides 2,4,7-tribromotropone in 50% yield, and 4-bromotropone and 2,5-dibromotropone have been identified as byproducts in this reaction. It was also observed that tribromo substituted tropone provides a mixture of 3,5 and 3,6 dibromotropolones by refluxing with potassium acetate in acetic acid or butanol. You can see furthermore the tropone can be synthesized by bromination of 2-cycloheptane 1-one with 4 molecules of bromine in acetic acid. This yield 2,4,7-tribromotropone. The tribromotropone further is converted to tropone by hydrogenolysis in the presence of poisoned catalyst, that is palladium and barium sulfate. Here palladium is poisoned with barium sulfate, and this is used as a poison catalyst for hydrogenation. The interruption of the reaction after the uptake of 3 molecules of hydrogen will provide tropone. As shown, incomplete hydrogenolysis has yielded 2,7-dibromotropone. So we have to first of all control the reaction condition so that 3 molecules of hydrogen are taken up to get tropone. 2 routes have been described for the synthesis of tropone, in which 2,4-cycloheptadienone is a key intermediate. In the first route, a mixture of cycloheptadienones was to be produced in one step by Hofmann degradation of tropinone. And in the second route, the para-toluene sulfonate of 5-hydroxy methylcyclo 2-hexene 1-one was prepared and converted to unsaturated ketone by treatment with sodium hydroxide. This reaction is considered to proceed via nor-carin 3-one. The structure of nor-carin 3-one is in front of you. As you can see, we have used diazomethane for the ring expansion, and finally we have received a tropone. Now, other method to produce tropolones or tropone is from benzene derivatives. The ring enlargement of benzene derivatives has been accomplished by a reaction with diazoalkanes. The reaction of benzene with diazomethane takes place under the influence of ultraviolet radiation, and cycloheptatriene that yielded from benzene is then oxidized to tropolone by using potassium permanganate. So we can have tropolone derivative starting from benzene itself just in 2 steps of the reactions. Another method to produce these molecules are from purpurogallin. Pyrogalol is used for the synthesis of purpurogallin. The oxidation of this purpurogallin provide 30 to 35% yield of dicarboxylic acid derivative with small amount of the other products. The acidic derivative then loses carbon dioxide at its melting point and is smoothly converted to 4-methyl-tropolone. So here it is shown as how we can use purpurogallin to prepare the methyl derivative of tropolone. Again, this is a 2-step process. and the yield is only 30 to 35%. Now let's move on to the properties of these molecules. They behave like a normal alkene, or I would say hydroxyl compound, which will follow the properties of hydroxyl moiety as well as the properties of the alkene moieties and the ketone moieties. Let us see what all reaction we can get from tropone and tropolone. The first one is Azo coupling. A large number of tropolone derivatives are reported in which there is free fifth position which have been successfully coupled in alkaline solution with diazotized paratoluidine and several other diazonium salts. Because its 3 to 7 positions are lying unoccupied in tropolones, these can be easily occupied with the electrophiles, and these electrophiles can be the diazotized, or you can say it is the azo group, which can attack on these sites to give you the diazonium compounds or addition products. For example, the 4-tertiary butyl tropolone, which is an exception here, the steric hindrance may be too great and all of these substances give coupling product except this compound. So all the positions, that is starting from 3 to 7, can be coupled if there is no steric hindrance. So it is one compound which is known as 4-tertiary butyl tropolone. Because of the larger tertiary butyl group, it imparts a steric hindrance onto the position 5, and that is why azo coupling cannot take place at this position in this compound. Another reaction is nitrosation. When these compounds are treated with nitrous acid in glacial or aqueous acetic acid solution, they convert tropolones into 5-nitroso derivatives. The reaction proceeds in high yield, and the reduction of these nitroso compounds provides the best route to the corresponding 5-amino tropolone. So if you want to convert tropolones to an amino derivatives, this is the best route. And there is no interference from any other substituents in this particular reaction. When the 5th position is blocked, the substitution occurs at position number 3. And this may be possible, but 5-methyl and 3-nitrosotropolone, the only product of this type, is reported. Now in another reaction, we can do the nitration of these compounds using nitric acid. So we use nitric acid and glacial acetic acid for the nitration. Sometimes cupric nitrate and acetic acid can also be used for carrying out the nitration in these compounds. The main product that we get is 5-nitrotropolone, which is accompanied by a smaller amount of 3-isomer. So we can see that the electrophile is happy to attack at position 5 as well as at position 3 if given a chance with the rest of the positions which are unoccupied. So we can say that position 5 and position 3 are easily available for the electrophilic attack. The nitration of 4-methyl tropolone similarly produces 5, 7 and 3 nitro derivatives in the yields which is in decreasing order. That means we get maximum yield of the 5 substituted product followed by the 7 substituted product and the minimum yield in case of 3 nitro derivatives. Similarly, we can carry out sulfonation. The sulfonation of tropolone with sulfamic acid leads to 5-sulfonic acid, which is possibly accompanied by 3,5-disulfonic acid. When the position 5 and 4 position is blocked by an alkyl group or by any other substituent like halogens, the reaction takes place equally readily at position 3. 4-methyl tropolone yield a product which is 6-methyl tropolone 3-sulfonic acid. After coupling with paratoluene, paratolulyl diazonium chloride. So we can see that the preference for entering of sulfonic acid is mainly at position 5 and position 3 and a little bit at position 4. Now let us see halogenation. The halogenation of these compounds happens as mono, di and tri substitution. It has been studied extensively. Only 3 mono and 3,7 di substituted has been observed with the unsubstituted tropolones. Only diiodotropolone is doubtful case in which the position of second iodine is unknown. Rest of them generally produce 3,7 disubstituted halogenic derivatives of tropolones. Now, two reactions have been reported which yield predominantly the 5 halogen derivative. Number one is 5-bromotropolone, which is obtained after the reaction of cupric complex of tropolones with bromine. And the second, the sodium salt of tropolone reacts with iodine monochloride, which gives a mixture of 5-chlorotropolone and a complex from which 3-iodotropolone is obtained by the action of water. Now, 3 and 7 substituted halogen derivatives of tropolones also occurred after the reaction of alkyl substituted tropolones with halogen. But a small amount of 5 substituted tropolones are also obtained. When 3 and 7 position are blocked, the 5 substitution occurs readily and we get 3, 5, 7 trihalogen derivatives which are readily obtained when these positions are not blocked in case of excess use of the halogen compounds. So, we can see if we are starting with the amino derivative of tropone and do its bromination in presence of sodium acetate and chloroform, you get 7 bromo-substituted tropone, and further bromination gives you the 5,7 dibromo derivative, which on further bromination gives you 3,5,7 trihalogen derivatives. Now, similarly, hydroxylation. When we do oxidation of tropolones with alkaline persulfate, it yields a mixture of 3,5 hydroxy derivatives, not exactly 3,5, I should say 3 and 5 hydroxy derivative. That means the introduction of monohydroxy groups in which the 5 product is predominant. That means the attack on the position 5 is more, I would say, preferred over the position 3. The 5 hydroxy tropolones and their ethers are also obtained by diazotization, as well as hydrolysis or alcoholysis of the corresponding 5 amino tropolones also give the similar product. Now, when we carry hydroxymethylation of these tropones and tropolones, this reaction is carried out with alkaline formaldehyde solution. Formaldehyde is a very good hydroxymethylation agent. So, we use alkaline solution of formaldehyde for hydroxymethylation of tropolones, and this reaction is carried out at a temperature of 60 to 65 degrees Celsius. Here we get 3 substituted product which is formed as a major product, whereas the di and tri substituted products are also formed during this reaction. Now, identification of these products has been carried out by the reduction of these hydroxymethyl derivatives with hydroiodic acid, and this is reduced to their corresponding methyl tropolones, and their rearrangement to methyl benzoic acid will be able to give us some characteristic feature, or will be able to make it easier to characterize these compounds. Now, let us see some of the natural products where these moieties are present. The tropone moiety has been found in several natural products. The alkoxy group and the alpha hydroxy group containing tropolones are very common in nature. The simplest tropolone isolated from Pseudomonas lindberghi, which is coded as ATCC 31099, and Pseudomonas planteri, which is coded as ATCC 43733. This simplest tropone is not a naturally occurring compound. It has been used as a basic building block in various cycloaddition reactions, whereas the naturally occurring tropones are relatively rare. The simplest tropone is nuzocone. The structure of this is given in front of you, which has got isopropyl moiety on the position number 4. In case of tropone, it's a tropone derivative. It is called nuzocone. and it was isolated from Thuja sand species. Now some tropone have amino or thio group rather than hydroxyl group. For example, methylation A, whose structure is given in front of you here, it has an amino group rather than hydroxyl group. And this compound was isolated from Dulacia guineacis. There are antibiotics, tropodiathetic acid and its valence tautomer thiotroposin, whose structure is also given here, have either thiosubstituents or a carbon sulfur double bond in their structure. So here are some naturally occurring compounds where tropone and tropolones moieties have been seen. A very unique fused tetracyclic carbon skeleton was found in a diterpenide tropones. For example, shown here are the structures which are tetracyclic in nature. Some diterpenide tropones have been isolated and they are characterized thus far as harringtonolide, hyanonolidol and fortunolide A, fortunolide B. These are having some complex structure, but you can easily identify the tropolone and tropone moiety in these natural compounds. And there is another one which is known as 11-hydroxy hyanonolidol. All of these are naturally occurring compounds containing tropone or tropolone moieties. Harringtonolide was first found to inhibit the growth of beans and tobacco. Subsequently, more interesting biological activities have been discovered of this compound, such as antiviral activity, antifungal activity and anti-cancer activities. So we can see that these compounds are biologically active and can be used extensively in the pharmaceutical research area. Now benzotropolone, the structure of this is shown here, is nothing but your purpurogallin. This contains a benzo fused tropolone core, right? We can see a benzene structure as well as a tropolone structure sharing the 2 carbon units, and hence they are called fused rings. Now this purpurogallin is the most common form of this family. It is a reddish crystalline substance isolated from nut galls and oat bark. Mostly these are obtained from trees. This is used as an antioxidant in non-edible oil, fuels or lubricants. Now thiaflavins family have also benzotropolone skeleton. You can see the structure of thiaflavic acid or thiaflavate and thiaflavin. All of these structure contains benzotropolone skeleton, and the benzene unit is often the part of flavones moiety. These thiaflavins are found in black tea leaves. Okay, so you have studied now some of the natural compounds wherein these tropone and tropolones have been found. These moieties have been found and they show some antiviral or antifungal activities, so they are biologically important compounds. Now let us summarize what we have studied in this module. We have seen that tropones and tropolones refer to non-benzenoid 7-membered aromatic compounds. It carries a carbonyl group which is also called troponoids or tropolonoids. Tropones or tropolones are classified on the basis of their natural isolation. These molecules show various types of reaction such as Azo coupling, halogenation, hydroxylation, hydroxymethylation, sulfonation, etc. These tropones and tropolones are also present in various naturally occurring compounds which are biologically important.